So hello and thank you for joining us. My name is Erin Wozni. I am the Business Development Manager over here at Softree. With me today is David Mills, one of our software engineers.
Good morning.
And we're going to be looking at working with LiDAR and improving your road design workflow. The increasing use of LiDAR in the forest industry really has opened the door to new software tools for road planning and causing us to really rethink what the workflow is that we're doing. So we're going to be taking a look at that. And let's get started. So I'm sure, as most of you already know, road construction is one of the most expensive components of timber harvesting. Forest roads are a major source of disturbance in forest development. The alignment of the road affects the natural slope and drainage and increasing the chance of soil erosion and landslides. So the location of these roads is really important. The goal of today's webinar really is to show you some engineering tools and a new workflow that are going to help you to find better road locations. And in doing so, reduce your construction costs, reduce the environmental impact, potentially reduce some of the cycle times for your trucks out on these roads, improve the safety of them, and probably the most significant of these benefits in terms of what we can help you do from a software side is the reduction in overall engineering time to build your alignments. So how are we going to do it? LiDAR really allows us, by giving us accurate geographical data, to maximize our pre-planning that we can do before we even go out into the field. So with that, we're going to be putting forth a new methodology for designing and planning forest roads using this LiDAR data and our mathematical optimization software, which is Softree Optimal. So the workflow, if we want to take a look at it before I pass it to Dave for him to actually demonstrate some of this to you, really in the past has been scouring your terrain photos, your terrain maps, your air photos, and other data sources to try and get a rough idea of where you want to go. But now with LiDAR, we're able to very quickly locate and optimize alignments using Softree Optimal, comparing our costs and quantities, and actually have a sense of what the geometry and cross-sections are going to look like for these potential roads. And I think I'm not doing a very good job talking to the ability to locate them, but we're able to very quickly compare what the costs and cross-sections are going to look like for a whole bunch of different alignments. And Dave's going to show you that today. So all of this is being done in the office before you head out into the field. And of course, you can prepare some maps and design data for field use. But really it means that once we actually get out into the field, put our boots on the ground, we're not looking at a massive area. We kind of have a sense of where our road is going to be. And it becomes much more about route confirmation and a lot less about reconnaissance, reducing the amount of field time that you're going to spend looking for different routes, allowing you to spend more time focusing on identifying unstable soils and regions, streams and wetlands, as well as potential pit locations once you go to start building your road. And with this process, you can have assistance from LiDAR-enabled in-field solutions. For those of you who didn't know, RoadEng actually is able to run on Windows 10 tablets. So you can have your LiDAR, your data, all of your plans and profiles that you've developed in your planning phase, you can actually have them out in the field with you. From there, you can go on, you're going to be doing your centerline field survey. One of the biggest benefits of LiDAR is you can actually use LiDAR for your side shots. Again, reducing the amount of time we're going to spend out in the field, which is significantly less time intensive compared to an L2 side shot survey. And then finally, the phase that most of our customers, as well as just other folks in the forest industry, are used to, and that's going back into the office with all of your data and designing your final construction and design documents. So this is your geometric design, plans, profiles, and cross-sections. And we've actually already done a bit of this work already in our pre-planning. We're just now making some adjustments if we found some unstable areas, and we can do a final optimization. And I keep talking about a word, optimization. Don't worry, I'm going to get to defining it a little bit better at a moment. But the last piece here, too, is we can get our final construction quantities and a really good sense of what our updated costs are like. So with this workflow, I mentioned design optimization, and really this refers to the process where we can look for the lowest cost alignment which satisfies our constraints and standards. It's automated for the most part, and it's now available as an add-in into road eng. It's called Softree Optimal. And if you're using another design program, such as Civil 3D or Inroads or something else, you can get this program actually as a standalone that can work with those other design platforms as well. And just to kind of quickly demonstrate a concept that Dave's going to talk about today, I'm going to use my really high-tech looking, very basic graphical model here in PowerPoint. But route selection using vertical optimization software really becomes quite interesting, and you can start to explore a whole bunch of different options. So let's say we want to go from point A to point B. We've identified these 2 points. We're going to peg in just the horizontal for route option 1, and Dave's going to demonstrate horizontal pegging today for you. And literally, with the push of a button, we are able to generate the vertical alignment. We didn't have to go through and add in any of the IP points. The software actually can automate that for you. Sorry, and then we're going to do option 2. But in both cases, using Softree Optimal, we're able to automate that creation of the vertical profile and really quickly start to get costs. And knowing our cut cost, our fill cost, and not just end haul cost, but our overall haulage costs, we're able to start to make really smart decisions with which is the better route to take. And from here, of course, then we move into that next stage of planning where you get your boots on the ground, you verify your route, and the process that most of you are used to. So with that very quick introduction, I'm actually going to pass it over to Dave. He's going to take you into the software, and we're going to go through an example of LiDAR and some horizontal pegging.
Thanks very much, Erin. And there we go. They're looking at the location module. And actually, I'm going to flip over to the terrain module first and show you our a piece of LiDAR that we've had here at the office for quite a little while. It's not the steepest of LiDAR, but it sure gives you an idea of how it can work. So if I were to bring in a new piece of LiDAR, one of the things I need to worry about is the actual size of the data. So I'm not going to follow through with this, but if I were to go File, Insert File, and pick my LiDAR XYZ files, this is kind of an unusual piece of data in that it's all in XYZ format, ASCII format. Usually LiDAR comes in LAS or LAZ. Nonetheless, they're big. Okay, I want to read those into my file, and I'm a little bit worried about the size of them, and here's the trick. I go into my selection tool, and if I'm doing an first stage kind of let's take a look at the data, I might just read in 1 in 10 or 1 in 20 points. So here I've reduced the quality of the import. I'm just skipping points randomly. There's a more accurate way to do that. I can go into my selection tool here. I can add a corridor. So this requires that I have a feature in my module already. In my terrain module, I have a feature, Route 1, for example. That's a road feature. And because I know where it is, I can say, give me points that are close to that feature, 100-meter corridor or 50 meters on either side of the feature. Now I've created this thing, I can say, well, read in all the points in the corridor of interest and skip most of the points outside the corridor of interest. Let's just skip ahead and I'll show you the results for that. So in this particular file, it doesn't count points with an ASCII import, unfortunately. The LAS and LAZ will show you how many points are in the file. There's a lot of points that I could have read in. In fact, if I select all the points here, you can see the final results. So what I did is I generated a import that read in 2 corridors at high resolution, and outside those corridors I read in at lower resolution. Obviously this is something you do after you've decided where your routes go, so I'm kind of putting the cart before the horse. But we will come back to that later after I've done the pegging. Okay, so now I have a LiDAR file. It's got a surface in it. I just used our calculate tin operation here to generate triangles and contours. It takes about a minute to put all these contours in there. And I've got these lines in the background. That's kind of cheating, Route 1 and Route 2. Let's pretend we don't know where those are. And imagine the process of designing an alignment from, as Aaron was saying, A to B. Okay. So that's LiDAR import. I skipped over a lot of stuff. The main point here is that LiDAR files are big. I've got over 1 million points in here. Many of them are contour points, but the LiDAR data itself is on the order of 1 million points. And our software handles up to about 5 million without too much trouble. So if you find you're reading in your LiDAR files and there's 10 million points per tile and you got 20 tiles to read in, well, you're not going to read it all in at once. You're going to use that thinning process to bring in data in an area of interest. And you can thin to a quarter, you can thin to a polygon, and you can even skip points entirely outside your area of interest. Now let's go to the location module and start with a new design. I'm going to use the original ground that I was just showing you and create a new alignment based on that topography. I'll just put my starting point in the middle of the alignment. Of course, if I had an existing desired alignment, for example, land XML, or even a terrain feature that was going where I wanted to go, I could use that as a starting alignment. But I'm going to draw the alignment. That's the point of this exercise. When I create a new location design, I am reading in my normal template table, so that's what the cross-section looks like in my default setup. I've also read in the terrain. There it is in the background. And I always get normal DLT as a starting point. That's a screen layout. I'm going to bring in another screen layout here, and you'll see that that will update my window locations. So this is what I call the pegging screen layout. Let's move the starting point from here over to the intersection of my two roads. That's point A. Like I say, I'm cheating. I want this to go fairly quickly, so I'm going to use those lines to help me design my road. Anybody with any experience in laying out roads on greenfields or virgin territory knows that it's an art. It takes time to decide where the alignment should go. You need to know a little bit about the terrain first. Topographic map is a start, but it's not everything. And there's a lot of tricks involved. But there's new tools inside location design that help with this. Create a new point, anchor it down. Instantly I see that that's a grade of 0.3% downhill. So all I did was I turned on a label in my plan window called horizontal eyepiece. No, that's not the one. Here we are, L-line grades. And when you've got a grade line, when you've designed your profile, that shows you the grade of the profile. But in this situation, I don't have a profile design. My vertical alignment is showing the ground, nothing else. There it is. There's the ground. And this is showing me the grade between this point, the beginning, and that intersection point that I just put in. So I can very quickly click around and find where I want to put my alignment. So let's say I want to go down this hill. I click here. Oops, that's minus 12%. Move it over to here. Oh, now it's minus 8%. That looks like a better spot for it. And then I can fine-tune it too. So if I put in a long piece of tangent, I may notice that I'm getting quite a bit of bumpiness in there on my profile, and I might want to fine-tune my grade so that it's actually tracking the terrain better. So let's look at the top here. Actually, I don't see an obvious spot where I want to make a change right now. Maybe I want to try and lift that gully up a little bit. So I'll go in here and I'll move that to there, and I'll move that down to there. Oh, that looks a little smoother. Like I say, it's an art. It takes a while. But when you have this grade label turned on and you're looking at the profile You're looking at the cross-section so you can see the side shots. In fact, I think I've got the profile set up to do that as well. These are side slopes, left and right. It doesn't take long to design on your computer a road center line. And that, I think, sums up the pegging part of the demo. Now I'd like to move ahead. I'm going to open up an existing alignment here. I'm going to open Route 1, which is the northern route. And kind of looks like this. And you can see the southern route faintly where my mouse is going. So the northern route has been designed. Not only are there tangents in there, but there's also curves. I've got the labels turned off right now, but if you turn them on, there's all my horizontal curves. So traditionally, you would design your vertical alignment. And I've done a hand design in here. I've gone through and I've picked intersection points with my mouse, and I have carefully designed curves on each of them using our vertical curve panel. So it doesn't take much effort. Let's say, for example, this curve here, I would like to change the K factor to be larger, so I'll just type in 12 there and apply, and that curve gets a little bit longer. Now, if you've used RoadEng, you know that you get all kinds of feedback while you're designing. For example, this mass haul diagram is being kept up to date. I've got a new diagram in here that is associated with the optimization software. It is essentially another way of showing material haul, free haul, overhaul, and all that's being kept up to date as I design my alignment. If I click anywhere in the alignment, I can see the cross-section, plan, profile, etc. There's even a 3D view if you want to see it. Let's just look at a quick 3D view here. Has to make an image of the background terrain, so it's taking a little bit of time to do that because there's so many points in there. And you can see that, you know, there's my road. Where it's green, that's where you're looking through the top surface, the original ground, and you're seeing the road underneath it. Where it's yellow, it's above the existing ground, and I can kind of poke around in here and see what my design looks like from 3D. Okay, close that window for now. And go back to my design. Okay, so I'm designing this alignment by hand, and I'm getting results that I kind of like. The optimizer, which we're going to look at in a minute, hang on to your horses. The optimizer requires me to know the cost of any alignment right now. Otherwise, it can't do its job. Optimizers all minimize something, and in our case, we're minimizing the cost. So I've got the vertical alignment here. How much does it cost? Well, I can set up, this is the old RoadEng ground table. If I click on that, you see the familiar slopes and expansion compaction factors and list of materials. In version 7, you now have the ability to attach a cost, cut, and fill cost to every material, and you can also define haul costs. One of the first questions we get as soon as I introduce this is, how do I know what those numbers are? And the answer is, first of all, use the defaults. They're not bad. When you open up location design in the new version 7, if you haven't already got it, it will put default costs in all your ground tables as you open them. Secondly, these numbers can be fine-tuned later as you become more familiar with the actual dollar values that you're producing. And thirdly, the cost is a great comparison tool, even if it's grossly wrong. I mean, even if 69,000 is double what it should be, it's still going to tell you when things get cheaper or more expensive. So as a comparison tool, you don't have to get these numbers perfect. You just need to be in the ballpark. Okay, so I've got costing tool here. every time I make an alignment change, it's going to recalculate the cost. Now you can do that manually by clicking on recost, or you can turn on this checkbox, which will do it automatically every time I make a change. Depends on the size of your alignment. I'll just demonstrate. So here's my hand design that I just created. What happens if I take this little point here and move it up a little bit? Click, recalculate, recost, boom. You can see the mass haul diagram changed, the haul graph changed, and the cost went up by a lot because I just created a whole bunch more fill, and it had to borrow it from this pit over here, and I've now got an unbalanced road. Okay, let's undo that. Okay, so far I haven't used the optimizer. This is all available in RoadEdge version 7. So you can use this recost tool to help you fine-tune your design. And as you change your alignment, you can watch that cost number, and if it doesn't go down, you probably made a bad change, unless of course you're doing it for safety or standards reasons. Now let's get to the interesting part. If I was designing a brand new road, and I wasn't really sure where I wanted to put it, doing a vertical alignment would really slow me down. It takes time to put that in. So let's not. Let's remove that vertical alignment. No, I'm not going to remove it. I'm going to leave it there for comparison's sake. I'm going to create a brand new alignment. This is also new in version 7. You can have multiple alignments, multiple vertical alignments. And I'm going to call it quick curves. And I'm going to generate vertical curves, 20 meters long. Here are my standards that I've set up beforehand in my original design here. -11, +11 grade, sag and crest curves. These are all things you can change. You can even change them by station range if you want. I've already set this up correctly. Control points. In this case, I'm going to set the starting elevation with a minimum grade of 5%. Could be -5, doesn't matter. Starts at 0 ± or -5. That's a control point. You can use control points all over the alignment. Typically, they would be bridge abutments, culvert cover, intersecting roads, overland fill depth. If you want, there's another way to do that. You can add other constraints, for example, full bench, minimum fill. I'm just going to put in the bare minimum here. I'm not even going to bother with a pit because this road actually balances pretty well. But you can add pits as well. So what have I done? I've created a recipe for designing the road, and now I'm going to just do that. Okay, so I'm going to calculate an optimal alignment. This part takes a little while. What it's doing now is it's calculating every cross-section that it thinks it might need. And I don't know if you noticed while I was going through there, but I did actually have a ± 10 meter specification for vertical offset. What that means is that the optimizer is going to try up 10 meters and down 10 meters, and it's going to calculate all the cross-sections in between with a little space. So we're essentially digitizing the whole possible road space in the vertical dimensions, station elevation dimensions. Once it's finished calculating all those cross-sections, then it can try various cross-sections. As you've seen, it can calculate cost very quickly, so it's just looking for the minimum cost. It's pretty smart. It doesn't just try every possible alignment. We're using something called mixed integer linear programming. We've got a very powerful open source engine called CBC, which comes with the software. And we've even got licensing rights to IBM's CPlex solver, which is an additional cost, but it runs a bit faster. So with all that technology behind, the software is able to calculate an alignment. Let's see what it looks like. So I've calculated a new alignment. You can see it there in green. The old alignment is still in red. Let's set the new alignment current. So multiple vertical alignments is new in version 7. And if you recall, my old alignment had much bigger mass haul excursions. The biggest one here is only a couple of thousand cubic meters. Or wait a minute, 600 cubic meters? Because, yeah, it goes station elevation, or station volume, sorry. Let's just maximize that. And there's not much movement. Look at all the curves. There's a zillion curves. So that's the downside of this optimization. But it's perfect for our task. I don't care about those curves. Let's just turn that off. What I have here is a proposed alignment that tracks the optimal alignment as closely as it can and gives me a whole bunch of information. Number one, cost, $40,000. Number two, all the cross sections. You've got your slope stake extents. At any point I can look at a cross section, see what it looks like, and I've got a proposed alignment that is basically the baseline. That you will never, when you use quick curves, you generate an alignment that is pretty much the minimum of cost. It may not be practical to build with all those curves in it. That depends really on your construction technique, but you're not going to find an alignment using any method that comes out cheaper than this. So this is a great measurement, a quantitative measurement of the quality of the horizontal alignment. Okay, so I've got an alignment here. I could go on and create a better alignment. Let me just demonstrate. Do I have to open a new one? No, I got it here. If I were to go into what I've done in this particular example is I took my quick curves example and I made a new one, clicked on the new button here, and I changed the options slightly. This would be more of a final process after I've decided which alignment I want to use. And I put in curves and tangents and I ran it again. Okay, so be aware that you don't have to do back-to-back curves, but it takes longer to do this process. So let's come back to that. Okay, so here we are. I've done my quick curves. Notice right away that it's way cheaper than the hand design, like way cheaper. We've got a difference of 42%. Just to give you guys the benefit of the doubt, those road engineers out there who've been designing forest roads for years, I've seen lots of forest roads come across my desk that are much closer than 40% to the optimal solution. I've never seen one that was less. The optimal solution is always less. There are exceptions, and the exceptions are always because the hand design cheated. So if I were to go recost, check constraints, I would find that the hand design, which is cheaper than my optimal, had a bunch of warnings in here saying you've exceeded grade, you've exceeded curvature, you're deeper than you said you wanted to be, you're not in full bench, things like that. So given that the hand design matches the same constraints that we've defined here, grades, curvatures, control points, other constraints, the optimized vertical alignment is always cheaper. Okay, so now I've got a questionably buildable road, but I know that it's the cheapest road I could ever get on this alignment. Is it better than my other route? So if we go back to the terrain, here's Route 1, here's Route 2. Now unfortunately, location currently can only handle one horizontal alignment at a time, so I solved that problem by just running it twice. So I'm going to run location again, and I'm going to open up Route 2. By the way, if you ever see this error, maximum number of section points exceeded, it really is just a warning. What it means is that the cross sections that are being calculated to show your cross section in location, they're finding so many triangles in the LiDAR background that they're running out of points. But they're trying to go out 500 meters by default each side of the alignment. And it's very seldom that your road actually extends that far. 99 times out of 100, you can just ignore this. On those other situations, you can increase the number of points. Right, so I've opened up Route 2, and this is the southern route, and it gets to the same place. There's the northern route up there, and I've done a quick curve optimization. The key point here is that I used exactly the same standards and exactly the same control points and constraints, and I get a result, $32,000. That may be wrong by a factor of 2, but if it's wrong by a factor of 2, so is this one, which is $40,000. And clearly, my $40,000 road is more expensive than my $32,000 road. So let's give up right here on Route 1 and move to Route 2. That's the key point here. Now that I've found that Route 2 is the one I want to use, I can continue with my design, probably go out and do a field recce as Aaron was suggesting. I'm certainly going to want to walk that corridor and find out whether we're, you know, armpit deep in swamp down here, or going through an unstable slide down here. That's stuff that you sometimes can't see in a LiDAR survey. But assuming that the alignment is okay, I can now start doing my final design. So final design, one thing, first of all, you can now create multiple vertical alignments. And, if you have an optimized alignment, nothing stops you from tweaking it manually. I haven't done any vertical alignment here because I haven't had to, but there's no reason I can't just go in here and start aligning this. Actually, there is. If I try to edit this point, I get basically no movement because there's curves in the way. So to modify a quick curves alignment, you pretty much have to delete the curves. There's another way around that. I could have used a polyline design. I can modify it by hand. Often forest roads are designed with short straight segments instead of curves. And of course, if I designed curves and tangents, as we saw in that other alignment, then they would be modifiable too. Back-to-back curves don't move around much because they're bumping right into each other, and so trying to move the alignment messes things up. Right, but another thing that you can do comparing costs, this is no longer about route analysis, but what if I just wanted to find out what's the, I'm going to go back to Route 1 here. So here's an example where I've designed the thing using curves and tangents, and as you can see, there are curves with tangents between them in my optimal design. But I can easily go in and say, you know what, I don't want 2 curves here, I want 1. So I'll just delete this point. And, oh, by the way, let's look at the cost. 45.11 total cost. Okay, that's thousands. Delete that curve. And, whoop, that's changed my cost. I'm just going to turn off that auto recalc because it's taken a little while. And then I'm going to move this over here a little bit. I'm going to go back to vertical curves and put 1 curve on there at, how about k equals 12. Okay. Made a hand design. Oops, I need a curve on the next point. I deleted that when I made my change. And now we're back. Let's just recost that. It's now 47, so I went from 45.11 up to 47.95. That cost me a bit of money. But there's nothing wrong with making hand designs. Here's another interesting thing. In quick curve, that's cost $40,000. Curves and tangents didn't cost that much more. Remember, it was 45 before. What if I wanted to just try a different quality of road. Raise the standard. So I'm going to create a new one. It's called higher standard. And oops, change the options. What do I mean by higher standard? I'm going to change the K factor to 12. Notice that you can do sag and crest differently if you want. And I'm going to reduce the maximum grade to, say, 9. It's calculating a, no, it's done. This road is particularly fast for quick curves. The curves and tangents took, how long did that one take? I think I ran it for 900 seconds before I gave up, and it wasn't finished. It could have gone a little further. It shows an optimality gap of 9%, which means that the cost that I'm seeing there might be 9% higher than it needs to be. I just created a higher standard alignment. It took seconds compared to my quick curve alignment. What did that do? Okay, here's the higher standard alignment. It looks like this. It's also got lots of curves because I just wanted a quick result. So I went back to the quick curves format. And you can see that it's, yeah, it's still a balanced alignment. It looks great. And the cost is $76,000. That compares with the quick curve result. The K equals 6 curve and steeper grades, 50% more expensive. Just like that, you get a quantitative result. This is how much it's going to cost to raise the standard of your road. It may, like I say, it may not be exact numbers, but that percentage value is quite accurate. Okay, with that, I'm going to close down the webinar. Thank you very much, everybody, and we'll see you, I think, next week.
Thanks, everyone. Have a great day.